Okay, in lesson 2.2, we start to see the similarities between chapter 1 and chapter 2 because we start to solve inequalities. And what you're going to notice is that especially when we're focused on solving with just addition and subtraction, pretty much the entire process is identical with just one minor difference. And that's the fact that because when we get to the answer, quote unquote, it's really a solution set, not just a single number, we are going to take that extra step of graphing our solution set on a number line. Okay, we could also use a set builder and interval notations and such, but we're going to focus on just graphing on the number line to demonstrate the set of all of those solutions and differentiating that from an equation which only has typically one solution. Okay, so the properties that allow us to solve this way are very similar to the addition property of equality and the subtraction property of equality, except that these are the addition properties of inequalities and subtraction property of inequality, but they state the same concept or the idea, right? And that is that adding the same number to each side of an inequality produces an equivalent inequality. So essentially, the relationship between the two sides remains the same as long as you add or subtract the same quantity on both sides. So to use an example here, we have a statement that we know is true. We have -3 is less than 1. We know that that's true. And the idea is I could pick any number here. I'm going to pick 5, but you could pick anything here. And as long as I add the same quantity on both sides, the resulting statement should still be true. Well, let's find out, right? On the left, if I do a -3 with a +5, I get a 2. And on the left side, 1 and a +5 is 6. So the question is, if I preserve that inequality symbol in the middle, is this still a true statement? Is 2 less than 6? And the answer is yes. So it stays true. And I just randomly picked 5. You could have picked something else, and you would still see that the statement still holds true. Okay, let's try it one more time with a little or equal to bar. That really doesn't change anything about the relationship here and the use of the addition property of inequalities. So if we have that -3 is greater than or equal to -10, which we know is true, -3 is greater than, it meets that criteria of the two, then I can, again, add anything I want on both sides. This time, let's do a 9, sure. And when I simplify both sides, -3 and a +9 gives us a 6. On the right side, -10 and a +9 is a -1. Is +6 still greater than or equal to 1? Yes, it is. Okay, so again, I just picked some random numbers here. You could have picked anything. Those are just two examples. But to generalize this, the big idea here is that if A is greater than B, if an inequality has been established, then A plus any number will still be greater than B plus that same number. That's kind of the idea there. You can add the same quantity on both sides, and the inequality relationship stays the same or stays true. Okay. Same happens with the subtraction property, right? So if it states that if you subtract the same number from each side of an inequality, it'll produce an equivalent inequality. So essentially, the relationship is maintained. We have -3 is less than or equal to 1 here. We know that that is true. I can pick a number. We can try the 5 again or anything else here. If I subtract that from both sides or apply a -5 on both sides, -3 and -5 is -8 on this side. On the right side, 1 and -5 is a -4. The question is -8 still either less than or equal to -4? The answer is yes. Okay, so we're still okay there. Let's try one more. We have that 7 is greater than -20. We know that's true. And then I could apply a negative of any number. I'll try 7 here. Could be anything you want. Okay, and if I simplify that, the inequality relationship should be maintained. So let's look on the left, 7 and a -7. Well, actually, that's 0. Okay, and that's okay. It's okay if things cancel out on that side. You just write a 0 to hold that. And then on the other side, it's a -20 and a -7. That's -27. Is 0 still greater than -27? Yes, it is. So we know that that relationship works, and I picked those numbers pretty arbitrarily. You could pick anything you want there. To summarize that algebraically, the main idea is if A is less than B, then, or if any inequality is established, then as long as I subtract that same quantity on both sides, that relationship is maintained. Okay, and the same thing happens for the less than or equal to or greater than or equal to and so forth. Okay, all right, so let's try some examples. And we're going to be using those same inverse operations. Those properties are going to allow us to use the inverse operations that you got comfortable with in chapter 1 with equations. We're going to use those to solve and isolate the variable. And really the only added step is that once we have our inequality solution, we're going to want to graph the solution set. Okay, so look at number 1. We have x minus 3 is less than negative 4. Our goal is to get that x value alone, or that variable, I should say. So I'm going to look at what did they do to x? Well, they subtracted they subtracted a 3, or they combined with a negative 3. That's what I want to undo. So I'm going to do the opposite operation of that. And if I do it on one side, I'm just going to make sure that I do it on the other side. Okay, so this should feel like deja vu. Like, oh, wait a minute, we just did this, because we did. It's exactly what we did with equations. I'm adding 3 on both sides or applying a positive 3. This is going to cancel. I get that x is still less than, right? Because that addition property of inequalities says that the relationship will stay, the same. So it'll still less than. And then negative 4 and a positive 3 is a negative 1. So that is the solution to this inequality. But we've got to understand it's not just, it's all the x's less than negative 1. And that is an entire solution set. There's a whole lot of values that fall into that. So not only are we going to write our solution there, but we're going to graph it. So now what we do, this is the only step that's really different than what we did with equations, is this extra step of graphing our solution set. So we practiced this in the last lesson. If my solution set is all the x's less than negative 1, I'm going to put a circle on that boundary number of negative 1. In this case, I'm going to leave it open because it's not or equal to. And then I'm going to shade in the less than direction, which is to the left. Okay, those are the numbers that are less than negative 1, are the ones to the left of the negative 1 on the number line. Okay, let's try number 2. We've got negative 3 is greater than negative 3 plus h. Okay, so this is where my variable is this time. So this operation that is next to it, that's what I want to undo. Okay, I want to get h alone by undoing this addition of the negative 3. Okay, so when I think about, well, they combined it with a negative 3. What's the opposite of that? Always look at the sign in front. This is a negative 3. And so this is going to now be a positive 3 on both sides of the equal sign. That's what's actually going to cancel this. Don't look at the sign behind it. I know it looks kind of like an addition, but that positive belongs to the h. If I'm going to get rid of this negative 3 that's not connected to h, I'm going to look at the sign in front, and I'm going to do the opposite. That's what's going to cancel the 3 on the right side. Now, on the left side, negative 3 and positive 3, oh, those also cancel, and that is okay. When everything cancels, we just write a 0, right? So I have nothing left on the right side. I'm going to have a 0 there to say that. My symbol should still be maintained. It should still be greater than. And then on the other side, I just have h. Okay, now this brings up a really important point, and that is that inequalities can get pretty hard to read if the variable is on the wrong side, meaning the right side. So this says 0 is greater than h. That can be a little confusing. If we see that greater sign, we might be tempted to shade to the right or make our arrow to the right. And that is incorrect in this problem. This is saying 0 is greater than h. That means h has to be less than 0. So it's a lot easier to read, and I'm going to expect it every time. So let me be very clear about that. That if your variable is on the right side, that you rotate this entire statement. Just rotate the whole thing so that it's easier to read and understand and interpret. Okay? So notice I rotated everything. The h is now on the left. Notice that the little arrow is still kind of pointing to the h and opening toward the 0. So I literally just rotated the whole thing, and then it is still accurate. This says the same thing, but it's more clear. This really tells us h is less than 0. Okay? And now I can go ahead and graph that. So if I put my 0 here, you don't have to label necessarily every single one of these, but just to kind of establish a pattern. And this is going to be an open circle on that 0. And we are going to, now we know, oh yeah, it's less than. I really should be shading in this direction toward the left, and then you know you're okay. Okay. All right, let's try on the other side, number 3. Now, just like with the equations, we want to make sure both sides are simplified before we start playing that whole inverse operation game. So I want to notice right away that I have a couple of like terms here that I can clean up before I really do the work here of solving. Okay, so I still have the 12 less than or equal, but I know that 4c and negative 3c is just 1c. All right, so I can bring those together and write that a whole lot more simply as just 1c, or c, plus the 10. And then I can start talking about, now that it's fully simplified, now we can go ahead and start isolating the c. That means I have to get rid of the 10. If they combined it with this positive 10, I am going to simply do the inverse of that, which is combined with a negative 10. Just knowing that these will cancel and that will leave that c value alone, that my inequality will be preserved. And then on the other side, 12 and negative 10 is 2. And then, like we said a moment ago, we will want to rewrite that and rotate that whole statement so it makes a lot more sense to us. So really our final answer should read c is greater than or equal to 2. And then we can graph that. So now I can come here and kind of pick a few values here to establish a pattern. It doesn't have to be every single one. My boundary number is a 2. This time, that 2 is going to be filled in because it's all the c values that are greater than or equal to 2. So 2 is part of the solution set, and everything greater than 2 is also part of the solution set. So that would be my graph right there. Okay. All right, number 4. Same idea. Make sure that both sides are fully simplified. I notice right away I've got some like terms right in here that I can combine. So the 15 is not a like term, but negative 7p and positive 8p, I know I can combine those into just 1p. Okay, and then greater than, and then constants also can be combined, right? So I have 15 ones and then negative 2 ones. Those are just constant regular numbers, but I can combine them together. 15 minus 2, I know, is 13. And all of a sudden, this problem that started off looking pretty messy is looking much better now. Okay, so now we can isolate p. If they're combining with a positive 15, we'll just do the opposite sign. That's the name of the game in this particular type of problem. So this cancels out what was with p. It helps us isolate it. And we get a statement here that says that p is still greater than, that symbol still holds true. And then on the other side, we have 13 and a negative 15, which will end up with the negative 2. So that is the solution set here, is all the p-values that are greater than negative 2. And then we graph it. So I'll establish where my 0 is, negative 1, negative 2, negative 3. Just come up with a few numbers here to establish a pattern. Find your boundary number. In this case, it's that negative 2. Open or close circle here? Well, it's all the p's that are greater than negative 2. It doesn't say it's including them, so I'm going to leave that as an open, empty circle. And I'm shading to the right. Okay. So we have all of those values that are greater than negative 2 are now shaded in. Okay. If we feel good about that, then let's remember and practice a little bit the vocabulary that lets us set up some of these inequalities, because we're going to use that in just a moment for some word problems. So quick practice here on just the vocabulary. We're going to just take the given statement or sentence, write it as an inequality, and then solve that inequality. So number 5 says the difference, and right away we know this means subtraction, right? So that's subtraction. So the difference of a number, okay, we don't know what that is, so we're going to say x or n, and 9. So the difference between a number and 9, that's difference between a number and 9, in the same order they gave it to you, is fewer than, so here's our symbol, fewer than, actually, here is fewer than, that means less than 4. So there's our inequality. And it said write a sentence, then solve. So this would be answer number 1. Answer number 1 would be writing that inequality properly. Okay, so that states exactly the same thing as the word English sentence said. It's the difference of a number in 9 is fewer than 4. Okay, and then step 2, or the second part of this problem, is to actually solve that. So let's come here. If I take that inequality and I solve it, I would have to add, or combine with a positive 9 on both sides. Okay, so that cancels. I get x is less than, and my new value on the other side is 13. So the solution set is all the x values that are less than 13. I should be able to pick any number that is lower or less than 13, plug it into this other equation over here on my left, and it should work. It should make it true. Okay. All right, so there's the 2 answers I'd be looking for on number 5. Let's try number 6. 6, so that's just the number 6 here, is less than or equal to, so we know that's the less than or equal to symbol, the sum, so that means addition, of a number, that's our x, and 15. Okay, so let's try that out. 6 is less than or equal to the sum of a number and 15. Okay, so there's our setup, and that was part 1 of this, was being able to just write the inequality that is equivalent to the English sentence. 6 is less than or equal to the sum of a number and 15. And then in part 2, we take that inequality and we solve it to find out what solutions make it true. So this is where we will identify where x is. We notice that it's being combined with a positive 15, so we'll do the negative 15, and that gives us a negative 9 on this side. The symbol is still less than or equal to right now, and then the x. But we hopefully at this point understand that this is hard to read, and it really opens the door to a lot of mistakes. So then we will finalize this by rotating that solution, the entire statement, so it makes more logical sense when we read it. Our solution is really all the x's that are greater than or equal to negative 9. And there's our solution, the second part. Okay, so now that we're warmed up on translations, let's solve a couple of word problems. On number 7, you have $15 to spend on groceries. You already have $12.25 or $12.25 worth of groceries in your cart. So that's already done. We want to write an inequality that represents how much more money you can spend. Okay, so you're already planning to spend $12.25. The question is, how much more? So what can we add to that? How much more money can we spend? How much can we increase this by? Right? But still be able to afford it, right? Nobody wants to get to the checkout counter and, have that awkward moment of like, oh, I don't have enough money to pay for what I, put in my cart. So you're already spending $12.25. How much can we increase that by, right? Or how much can we add to that? But stay in budget, which means that our total here has to stay less than or equal to the $15 that's in our pocket. That's the big idea there, okay? And so this is what that inequality would look like. We would establish how much we're already spending, set up an expression that says how much more can we add to that, but that will stay under or equal to the $15 we have. So that's part 1. And then in part 2, of course, we take that and we solve it like we did earlier. So we're already spending $12.25. We're going to spend a little more, but make sure we stay in budget. Then the idea is to find this difference and say, okay, well, if I am already spending this $12.25, how much do I still have, or how much can I still afford, right? So since we're dealing with some decimals, we will add a couple of zeros after a decimal there to kind of make things easier. That's going to leave m by itself, less than or equal. And when I do this math here, I'll borrow, make that 10, make that, so I've got 5, and then, what is that, 9, 7, 2, and nothing. So there it is. So I've got to spend less than or equal to $2.75, or basically that's what I can spend. So I can spend, and listen carefully, if you get nothing else out of this video, this will help you a whole lot on our next learning checks and tests. I am going to be looking in your full sentences for the specific vocabulary that tells me you understand that this is an inequality. I don't want to hear, I can spend $2.75, okay? It's an inequality, and I want you to express that in your vocabulary. So I want you to say something like, I can spend at most, okay, $2.75. Or maybe you say something like, I can spend no more than $2.75. Something like that. But definitely your sentence should communicate to the reader that you understand that this is an inequality and there's not just that it's not just $2.75 that you can spend, but that is the most you can spend, or you can't go over that much, that kind of thing. Okay. All right. Let's try number 8. You order a new pair of running shoes from a website that offers free shipping and orders of $75 or more. Your shoes cost $69.95. So we want to write and solve an inequality that represents how much more you can spend to get that free shipping. Okay, so really similar to the last problem, we're already spending $69.95 on the shoes. And we want to know how much more can we spend with that, but still get the free shipping. So the free shipping happens on $75 or more. So basically, whatever this grand total is right here, this expression I just wrote, I want it to be more greater than or equal to $75, because then I will know I'll get my free shipping. So how much do I need to add to that to guarantee that the left side of this is greater than or equal to the $75, and then I'll get my free shipping. So that's our setup. And then we'll use the addition property of inequality and make this a little small here just so we can fit it when we solve it. And we'll find out what this difference is to find out what's the least I need to still spend to make this happen. I want to get a good deal here. That cancels. I'm subtracting this on this side as well. So I need to spend greater than or equal to, or at least, this difference. When I compute this out, it comes out to $5.05, if I'm not mistaken. So that is what I want to make sure is I spend at least another $5.05 in order to get that free shipping. So here's my inequality, and there's a solution to that inequality. I need to spend $5.05 or more if I want to get the free shipping. The second part says the cost of shipping your shoes is $7.79. Would you purchase another order just to get the free shipping? So assuming that it's not something you would normally buy, would you purchase another just to get the free shipping? Well, anything $5.05 or more gives me free shipping, but it doesn't make sense for me to buy something that is more than this if I'm just doing it to get free shipping. If it's more than $7.79, then I'm better off just paying for the shipping, right? So with that in mind, I really would only do this if I get something that kind of falls in between this. So my answer at least would be only if I can buy an item or items that cost between $5.05 and the $7.79. Right? I mean, that's not a 9, hang on. $7.79. So I want to spend more than $5.05, but no more than $7.79. If not, I'll just pay for the shipping. So it's really something in between there is really where I get the best deal, and I still get some extra item, but then I don't have to pay for the shipping on it, and that's kind of the sweet spot right there. Okay. All right, last one. On number 9, you're given that the perimeter for this triangle is less than 37.8, and we're wanting to solve for x here. So let's set that up. Remember, the perimeter is just the sum of the 3 sides. So if I add up the x value, the 12.5, and the 11.8, I know that the sum of the sides has to stay less than 37.8. So there's my perimeter. So perimeter is the sum of all sides equals perimeter, and in this case, we want the sum of those three sides to have a perimeter that is less than 37.8. And so now we just simplify like we did earlier. I can combine those constants there. So if I'd add the 12.5 and the 11.8, I believe that gives us 24.3. So now we simplify it a little bit like we did earlier on the previous examples, make it easier to work with. And then we use those inverse operations. If they're adding that 24.3, we will do the inverse of that to get that x isolated. Line up your decimals. Little decimal computation 101. That cancels on this side. X is still less than because we used the subtraction property of inequalities, so that should still be true. And this difference is going to be 5. Bring down the decimal, 3, and then a 1. So in order for this perimeter to stay less than 37.8, the side needs to be less than, or the unknown side needs to be less than 13.5 meters. There it is. All right, have a great evening.